So we'll go ahead and hop in right where we left off with the probability definition. We went over the notation and rules, and now we'll apply it with a short example with the wolves and coyotes that we've been talking about. Same data set the museum had gave us. We'll be applying rule 2 to the individual probabilities, as you can see listed here. This falls under the category of mutually exclusive events where the probability of a short coyote and a tall coyote can be summed up together. Since they're mutually exclusive, there's not an overlapping coyote that is both under and over 2 feet tall. And so we can just look at the state space and just check to make sure that our logic correct and make sure that they are mutually exclusive events. And it's true because there's no overlap between any of the classes of the tall coyotes or the short wolves. And so we'll go ahead and just state some facts about the problem, such that the probability of a short coyote plus the probability of a tall coyote equals the total probability of the coyote. Similarly, short wolf, tall wolf equals the probability of a wolf. And overall, the state space is talking about the probability of an animal. And so we can sum up the probability of a coyote and wolf, and it has to equal 1. And this is applying rule number 4 that we just learned up right here. So we're just systematically applying rules to the problem to formulate it such that we have some facts about what we're trying to calculate. And so we can go ahead and just begin enumerating some of these probability calculations. And so how to actually calculate the probability, for example, probability of coyote, we can use the state space diagram that we have drawn, the red and black diagram, to count the number of total events or total animals in the state space, and then overlap it on what are a specific class that we're interested in. So for example, the state space is representing animals, and we want to figure out the probability of a coyote. So we can count up the total number in the state space, and then the total number of coyotes, and then divide them. And so that's what we're going to do right here. We see the probability of coyote equals the number of coyotes over the number of animals. And so we can just sum it up right here in the table. We had previously noted that they were similar counts. And so the wolves and the coyotes both have 30 in their populations total. And so 30 divided by 60 equals 0.5. And that's the same as the probability of a wolf. Little logic check, this checks out because 0.5 plus 0.5 equals 1. So we're all good with rule number 4 and applying some of the notation that we had already laid out. Similarly, we can do a similar process for finding the probability of a specific event or the specific event of a tall coyote in our overall state space. So we will do the same sort of systematic application of counting the total number in the state space and then the specific class that we're interested in. And so since we're looking at the class of all animals, it's going to the state space of all animals, it's going to be over the entire 60 instead of just the number of coyotes, which is 30, because we're interested in what's the probability of a tall coyote given the whole population. And so we'll do number of tall coyotes, which you can find in the table right here. So we'll be doing number of tall coyotes, which is 6, divided by the number of animals, which is 60. And we see that it's resulting in a 0.1 probability. We can do the same thing with tall wolf, where we look at the table, we see that it's 18 for the tall wolf. So we can do 18 over 60, and this gives us 0.3. And so these are just some examples of how to just run through easy probability calculations. What we're going to be discovering is that using some of these just simple facts and just statements about our problem, we can derive something that's a lot deeper that can help us solve our problem at hand, where we've seen a tall animal and we want to identify where it's more likely to be a coyote or a wolf. So this leads us into something called Bayes' theorem, which is a key theorem in this course and is what you're going to be seeing a lot in next units with Bayesian networks, and also you'll likely see it in your statistics classes. But this applies some of the rules that we had noted before and uses algebraic manipulation of the probability to state it in a different way. And while this is just manipulation of symbols and probabilities to get us, a different representation, this different representation is often very powerful and can answer the question at hand that we're looking at. And you can see the applications further down the road with conditioning on features and machine learning, and we'll just continue to see how this creeps up over and over again. So this is like the first introduction. What we will notice is that from the rules that we stated above, the probability of two events happening, which you will write it in mathematical notation like this, where the probability of A, which is one event, can also, and B happening, can be written like this, where this is something called the cap. And so we're basically doing the set intersection. So we're trying to get what is the probability of both of these events happening. And so in the Venn diagram, this is could be represented. So we have the short guys on one. I'm not going to draw actually I will just go ahead and copy and paste this guy over here. We can just use this. So we're looking at probability of A and probability of B, where A could equal wolf, for example, and B could equal short. And so we're looking at probability of A, probability of B, which would land us probability right here in the state space. So this corresponds, this probability A intersection B, where A is the wolf, B is short. We can just look at the state space and figure out what we're talking about in terms of the data that we have and what this actually means from the mathematical notation. So it states from notation above that it is the probability of A intersection B is the probability of A, PA, which is written right here, times the probability of B given that A has occurred. So we haven't seen this notation before, so I will write it out. This bar can be basically represented in English or thought of in English is given. So what is the probability of B given A? So probability of B given A. So this is the first thing that you'll see with conditional probabilities, and we will see how we can use conditional probabilities to solve our problem. And so just using this statement of facts, we can, in these two classes, we can write it out such that our expression looks like this now, where the probability of A and B can be written in two different ways, where we have the probability of A times the probability of B given A, similarly probability of B and probability of A given B. And since we know that they are talking about the same area of our sample space, and we're doing essentially the same calculation, we can set them equal to each other and try to isolate one of the probability conditionals on one side and see what that means in the context of a problem. So some equal to both sides, we get this expression where you have the top equation on one side, the bottom equation on the other side. And this yields what we're looking for. It's called Bayes' theorem. And this isolates one of the conditionals on one side and enumerates an entire equation based off of the two class conditionals on the other. And so this may just seem like you're manipulating the variables or you're just moving them around, but how does this actually apply? So in our case, we're looking at probability, or we're looking at two classes, A and B, where A is the wolf, B is short. So if we just substitute what these A and B are with wolf and short, we can see that we're looking at now, what is the probability of a wolf given something that's short, for example. And we can directly calculate what that probability is, where it's just the probability of wolf, probability of short, given that it's a wolf, divided by the total probability of short. So this representation is very powerful because our question at hand is we've seen something tall and we are trying to find what's the most likely case, whether it be coyote or wolf, which is asking the question, what is the probability of this, which is just conditional. So now we have some tooling. We can represent the A and B with coyote, wolf, and tall for the B, and then directly calculate and compare, and that will be our solution. And so stepping into the math and just finishing off, our solution is represented by the probability of a wolf given something that's tall, and the probability of a coyote given something that's tall. And from Bayes' theorem, we know we can represent it such that this is the form of our two solutions. And we are curious about which one is more likely or which has the greatest probability. And so just like how we did it before when we were doing Bayes' theorem, we could just set them equal. We could set two equations on either side and begin comparing to see which one is more or less. And so we can just directly cancel out some terms that you'll see that are overlapping, and that'll yield our answer. So the probability of the wolf will be on this side, where I will write it out like that, just so it's very clear on which class is which. So that's coyote, and that's the wolf class. Okay. So what we're interested in is which one's more likely. So we can just directly start canceling out variables. So we know that the probability of a wolf and probability of coyote are the same because we did the calculation above, where the probability of coyote equals 0.5. So just from this first equation right here, we can look at both sides and see that on the top, there is the probability of wolf, probability of coyote. Since they are equal, we can just remove them from both sides since they are on the numerator. And that yields us with our second form, where we have a conditional probability of tall given wolf divided by tall, which is right here, is what compared to probability of tall given coyote divided by probability of tall. And so again, we can notice that we have two variables that are the same on both sides, where probability of tall is the same since we're talking about the same event in the same state space or sample space. So we can just directly remove it and get to our third statement, which is just the two conditionals, where we have probability of tall given coyote and probability of tall given wolf. And so now we're just left with just this pure conditional probability. How do we actually solve it? So we can consider the state space that we have been using and derive the probability from there. So we know that with the conditional probabilities, we are given something that's true. And so this restricts the sample space or the state space of which we're operating on to calculate these probabilities. And so when we are given or have the conditional probability, we can almost consider it as cutting up the sample space such that we're only considering a subset of it. And so when we say that we are given a wolf class or given a coyote class, we will only consider this side or this side of this division line. And so we still have to abide by all the rules and notation that we had demarcated up above, where the probabilities must sum to 1 and the probability must be between 0 and 1. And so how this works out is that our overall sample space can be represented smaller. And so we can just have a sample space of just pure coyotes and one of wolves. Tall, short, tall, short. And what do we know about these sample spaces? We know that there are 30 in each, and we know the counts of everything that's inside of it because of the data that the museum gave us. And so from that, we can just directly do some numerical calculations where we have defined these new sample spaces, and we have number of tall wolves given by the museum head, number of wolves we have calculated is what compared to the number of tall coyotes over the number of coyotes total. And since we knew before that the number of wolves and the number of coyotes are equal, we can remove them for both sides. And then it's very obvious on what the answer is, which is that there's more tall wolves than there are tall coyotes. And so it is more likely that the tall animal is a wolf. So we have just stepped through our first example on how to do these probability calculations, some of the notations, some of the rules. Now we'll do a tweaked example with the same data set or the same kind of idea with a tweaked data set where the population sizes are different. And we'll get motivation on how to begin formulating decision boundaries and how this can apply to other problems. So suppose that our population size is different, that over 1 year, the coyote populations increases threefold or fourfold, where before there was 30 coyotes and now, let's see, this is threefold, because now there are 90 coyotes and there are 30 wolves that are in the population. And so there's 120 animals total, but you can see that there's an imbalance between the wolves and the coyotes. And so how does this change our problem? Well, now that we've derived Bayes' theorem, we have a systematic formula for how to solve these problems. And we can just plug and chug basically with all of our new probabilities with this new problem. And so again, just setting it up, the probabilities that we are caring about is the probability of a wolf given a tall animal and the probability of coyote given a tall animal. And now the probabilities have changed, where the museum had given us new numbers, 90, 30, but note that there are number of coyotes and number of wolves that are tall are the same. So may not be so obvious what the answer is. We're just going to basically do the same sort of methodology that we did before, where we're going to go step by step on the equation representations, removing the known variables or stuff that's equal, and then yielding our final comparison. So we'll start out with the full expression, which is right here. I will again draw the highlights over it. So same thing as before. We're observing this equation. We can see that the probability of tall is the same on both sides because we're still talking about the big sample space that I will again, let me actually copy the one above. I'll copy the sample space. It's helpful to visualize. Cool. It's a little bit off balance now, but we know that the probability of tall is the same on both sides since we're talking about this overall space still. And so we can just directly cancel it out. And then we can directly do the calculations on the probability of wolf and probability of the coyote, just like we did before up here, where the probability of coyote equals the probability of coyote equals the probability of a short coyote plus probability of a tall coyote in this overall state space. Similarly, probability of wolf equals the short wolf plus tall wolf. And we have the overall animal summing to 1, just like rule 4 requires. And so let's go over here to our new problem and try to do those probability calculations. So we know that, let's do the probability of a wolf. It's equal to the number of wolves over number of animals. That equals now 30, 120, 1/4. So we know from the probability of animals that it overall sums up to 1. And so the probability of a wolf is equal to 1/4. We can just directly know that the probability of a coyote is equal to 1 minus the probability of a wolf, which equals to 3/4. Cool. So now we have the probability of a wolf, probability of a coyote. While they may not be equal, we can't just directly cross them out like we did before in the other problem. We know the relation between them, since one's 3/4 and one's 1/4. One value is 3 times the other one. Specifically, the probability of a coyote is 3 times higher than the probability of a wolf. See right here, just like the calculations that we just did. And so we can just replace the probabilities with just the multiplicative factor of the ratio, which is 3. And so now we have this expression where we have the probability of a tall wolf, 3 times the probability of tall given a coyote. So now we're directly kind of at the same stage that we were before, where we need to do these new state space calculations or sample space calculations given our individual wolf or coyote populations. And so just like before, it's the same representation where it's the number of tall wolves over the number of wolves. And then we have this 3 that we got to take into account times the number of tall coyotes divided by the number of coyotes total. And so we know that our coyote population is 3-fold greater than the wolf population. And so this actually comes into play where once we do the calculations, where we know the number of wolves is 1/3 of the number of coyotes, we can just cancel them out. And then it becomes a comparison between the number of tall wolves and the number of tall coyotes. And so if that didn't make complete sense, let's go ahead and just do the sample calculation right here. So we're looking at the number of tall wolves, which is 18, over the number of total wolves, which is 30. And this is what into relation to 3 times 18 over 90. And so I'll just write it over again, but now I will use this 3 to reduce the 90, where this just becomes 80 over 30, and you can see that they're equal. And so what does this mean? That it's equally likely that the observed tall animal is either a wolf or coyote. So this motivates some of the discussion that we'll be continuing to talk about this week, where we'll be now going into something called decision boundaries, where you can see that it was very obvious that it was one population. Now it's not so obvious. And as we continue to complicate the problem or change some of these variables, how does this boundary change where one class is more likely than the other of being a certain animal? So